Okay, so I just wanted to go over this worksheet with you to sort of see what I'm asking you to do. Okay, so we have a block. Oops, I'm moving that around. A block is suspended by a string. Get a pen. For each situation below, fill in the table given the quantities magnitudes below. So here are the interesting magnitudes that are given to you. Use the space below the chart to sketch FBDs as appropriate. Okay, so it's a block suspended by a string. So we've got mg down and we've got tension up. And we have 4 different situations. One, so I'm just going to do the whole row for this first situation. So you can just see what these columns are about. So it says it's going down, so that's V, but it's speeding up. If it's speeding up, then A is in the same direction as V. And so it looks like that, okay? So this thing asks for the direction of A, and so it's down. Now it asks for the direction of the net force. Well, we know Newton's second law says the net force is equal to ma, so those are going to be in the same direction. And as I just said, the net force, what's the magnitude of the net force? The net force is going to be equal to ma. Do we have m? We do, even though did we need it? I think you could have figured it out by that. But it's 2 kilograms. And the magnitude of acceleration is 2 meters per second squared. So that's 4 newtons. So the magnitude of the net force is 4 newtons. If you want like a little down again, just like here, that's cool. All right, to figure out the tension, we need to actually do Newton's second law. My acceleration is down, so my mg gets my positive, and then my t gets my negative. All right, mg minus t equals ma, so therefore t is mg minus ma. Mg is 20 newtons, and ma is 2 kilograms, 2 meters per second squared. We knew that actually already because that was right up here. So that's 16 newtons. So my tension is 16 newtons. This is the work done by tension. So the work done by tension is going to be T dot D. And so in this case, my T is up and my D, which is in the same direction as my V, is down. So that's going to get a big old negative out front. So it's negative 16 newtons, and then my D is 3 meters. So that's negative 48 joules. Okay. The work done by gravity, in this case, right, is going to be, right, mg down, v, and d down. So it's going to be positive, and that's 20 newtons, and that's 3 meters. So that's 60 joules. Okay, I'm going to try to move up for a second. Ooh. This thing kind of got jiggly. Okay, then the change in, let me get back to a pen. The change in gravitational potential energy is mg delta H. So mg is 20 newtons. Delta H in this case, because we're going down, is negative 3 meters. Great, it's final minus initial. So my final is lower than my initial. So you'll have a negative 3. And so that's negative 60 joules. You may notice the work done by gravity and the delta UG are the same number but opposite. That is very important, and we will get way more into that later. Okay, so now here it's asking, all right, remember that the total work is, it gives you that change of energy of the system, right? And that change of energy is going to be a kinetic energy. The total work is the change of kinetic energy. Actually, I'm going to change that. I'll go change it on the file too. So total work is the tension, the work done by tension plus the work done by gravity. So that's plus 12 joules. Okay, and then therefore, that delta KE is plus 12 joules. Now what's really cute, if you think about what is delta K, move this over. Delta K is 1/2 m Vf squared minus V naught squared. If you remember from your kinematic equations that Vf squared minus V naught squared, that's like your third kinematic equation, is basically the other side is 2AD. So your delta K is mad, all right? And if you put in these numbers, you get 2, you get 2, you get 3, you get 12. Yay! Kinematics and energy go nicely together. All right, so the rest of your homework is to do these other 3 rows.